Hey everyone, in this video I'm going to talk to you about lipids. This is a major class of biomolecules that you'll need to know some of the basics about. These are really high energy storage compounds. They actually contain the most energy per unit weight of any of the biomolecules, certainly more than carbohydrates and more than proteins. So lipids come in four sort of major classes. We'll go through each of these just briefly, just to show you kind of an overview. So first we have the fatty acids, next the triacylglycerols, phospholipids, and then steroids. So the fatty acids, let's take a look at the structure of those. Those contain a carboxylic acid, and I'm going to draw it as its carboxylate because that's what would be the charge at physiological pH. And these then have long hydrocarbon chains in them. So I'm going to draw palmitate, which is the C16 version. So this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so this is called palmitate. And you wouldn't be expected to memorize all the different names of the different fatty acids, but recognize that they could be different chain lengths. So you could have one with maybe 8 carbons, or 12, 16, 18, 20. They even go out to 40 carbons. So a fatty acid chain has a polar head group, okay, which is the carboxylate, and then it has a non-polar tail. All right, so molecules that have this type of structure where you have one end that has the sort of polar group on it and then a long sort of hydrophobic group, one that doesn't like to dissolve in water, these are called amphipathic. Oh, I spelled that wrong. A-M-P-H-I, sorry. Okay, which basically, again, just means it has both polar and non-polar regions. And when you draw out fatty acids, again, you can kind of envision them as sort of a long cylinder, essentially, with a polar head group. So we often would abbreviate this kind of something that looks kind of like that, if we were to draw a lot of these together. So when you take fatty acids and you throw them into water, what they will tend to do is they'll tend to clump up and form a structure called a micelle. And a micelle is essentially a collection of these that form sort of a spherical type structure. So I'm just going to try to sort of draw a bunch of these fatty acids. And what happens is the polar head groups, which are each negatively charged, those would reside on sort of the outside of our little droplet. So envision you have a little droplet of fatty acid in water. If you take a cross section of that, that's what this would look like. So the interior core is the hydrophobic region, where all of these long hydrocarbon chains would be sort of clustered on the inside. And then water would be surrounding the outside polar head groups, sort of hydrogen bonding to them. So this is called a micelle. And that's the structure that fatty acids would adopt if you were to throw them into water. One last thing we need to talk about with fatty acids is that they can be saturated hydrocarbon chains, or they could have hydrocarbon chains that have carbon-carbon double bonds in them. So again, this would just be palmitate with 16 carbons, no double bonds. But you could envision maybe having a double bond out here. And what I've drawn is a trans double bond. So this would have a trans orientation. Alternatively, you could have a cis double bond. I'm just going to erase this right here and put this group coming down like this. That would be an example of a cis double bond. Now in nature, when fatty acids are synthesized, almost all the time the fatty acid chains, if they're going to have a double bond, are in the cis format. Okay, and so this would actually be called a 1, 2, 3. If we count from the end, the methyl end, this would be called an omega-3. Okay, so we use the Greek letter omega, which looks kind of like a W. So this would be an omega-3 fatty acid. And omega-6 would have 1, 2, 3, 4, 5, 6. It would have a cis double bond at the 6th position, and so on. In general, cis fatty acids tend to be, I guess, the more healthy type fatty acids, whereas if you have trans fats with trans double bonds, those tend to be less healthy for you. And these cis and trans double bonds also affect the melting point. In general, cis fatty acids have low, I should say not boiling point, melting point. Okay, so these are liquids at room temperature. Conversely, fatty acids that have trans hydrocarbon chains or trans double bonds, those tend to have a little bit higher melting points, and they would tend to be solids at room temperature. All right, so that sort of summarizes the so-called fatty acids. They're kind of the basic building block. And in the next section, we're going to see that these fatty acids can be then joined to other molecules. All right, so the second class of lipids that we want to talk about are the triacylglycerides. And what these are, these contain a molecule of glycerol, which is a triol compound that looks like this. So this is glycerol. So now envision taking those individual fatty acids we talked about and adding one of those to each of these alcohols through an ester bond. So recall when you mix a carboxylic acid and an alcohol, these can react to make an ester. So here I have a fatty acid, this one here. So envision this R is this long hydrocarbon chain. It's going to now get connected to the first alcohol of glycerol. And we'll do that a second time, and then a third time. So each of these alcohols can then react to make an ester. And so if we now draw the resulting triacylglyceride, it would look like this. So we now have made an ester bond. There's our second ester. And here's our third ester. And we also get 3 waters out of this process. So in the synthesis of triacylglycerides, the molecule glycerol again is then esterified to 3 individual fatty acid chains. And depending on the cell's needs, the needs of the adipose tissue, which is where most of these are synthesized, or in the liver, they're also synthesized there. The R side chains could be the same, so they could all be like palmitate, C16, or they might be different. They might have longer or shorter chains than C16. So you could have a mix of different R groups in the triacylglycerides. And as you see, imagine now these have long hydrocarbon chains. This group here is the so-called polar head, and these would be the non-polar tails. But you've probably already noticed that because these are now esterified and don't have an OH group, these are not tremendously polar. Esters are not the greatest polar molecules, so these would definitely not like to dissolve much in water. So the polar head group, even though it does have oxygens, not really that polar. So when you put triacylglycerides into solution, they also will tend to form micelles, just like the fatty acid chains. And we often would sort of abbreviate this. We'd put kind of 3 tails coming off of each one. So envision now a micelle of these, where I'm going to put the sort of polar glycerol head groups, and coming off of each, I've got 3 little lines. Yeah, I won't draw all of them here, but you can kind of get the idea. So these long hydrocarbon chains are now embedded in the micelle. The glycerol polar head group is sort of on the outside, and then water would be surrounding it. And this would essentially look like a little oil droplet in water. So triacylglycerides are actually the form of fats that you would find in vegetable oil. So corn oil, canola oil, olive oil, all of those are these triacylglycerides. In mammalian systems, the triacylglycerides is what's found in adipose tissue. And it's kind of a mixture of sort of semi-liquid, sort of semi-solid components in actual adipose cells. So that's the triacylglycerides, and they, like the fatty acids, tend to form micelles. As we'll see in the last two types of lipids, what we're going to do is we're just going to change one of these positions on the glycerol, and it's going to dramatically modify the behavior of these when you put them into water. So the third class of lipids that I'd like to discuss are the phospholipids. So just like we saw before, we have this glycerol component. And for these, I'm going to attach two of the fatty acid chains to the carbon 1 and 2 of glycerol. But on this second one, instead of putting another fatty acid chain, instead, what we're going to do is put on a phosphate. And I'm going to just put R right here. The R could be an H. If R equals H, we just have a simple phospholipid. Okay, so in other words, if this is just a normal phosphate, we would just call it a phospholipid. I won't go too much into this, but cells can modify this R group and put other groups on here to sort of tweak the properties of the phospholipids. But one of the really interesting things that happens with phospholipids, as opposed to fatty acids and triacylglycerides, when you put these into water, something very dramatic happens. So I'm going to abbreviate one of these phospholipids like this. When you put these into water, what they will form, instead of forming a micelle, they will form what's called a lipid bilayer. Okay, so the long hydrocarbon chains do associate in sort of a hydrophobic core region, but the negatively charged phosphates that are here as part of this position, they tend to form a bilayer. So instead of forming a micelle, if you had a cylindrical one of these, envision now these being thrown into water. And what we would now have is a bilayer, where you now have sort of a hollow region in the middle. I won't draw all of these out, but this region in the middle is hollow. These are the types of lipids that are found in cell membranes. So envision now this is a hollowed out region. This is what a cell is. It's a lipid bilayer made of phospholipids like this that has both an inside and an outside of the sphere. So if we were to sort of do a cross-section of a spherical droplet of phospholipids, it would have a hollow interior. And this simple change of converting the triacylglycerides to a phosphate, it's thought that that's actually what helped cells to arise, is to be able to have this compartmentalized lipid membrane. So again, the normal phospholipids, just traditional phospholipid, would just have the R group would just be an H here. Again, there are other classes. We won't go into those too much, but if you put other R groups, you can sort of tweak the properties of these, and it makes the phospholipid bilayer maybe more fluid or less fluid. So this is a fairly flexible type membrane. So the bottom line is phospholipids are components of membranes. These would not typically be thought of as the storage form of fats. Those would be the triacylglycerides. All right, and then the last section we're going to see, we're going to look at the so-called steroids. Those are completely different than any of the ones we've talked about up to this point. The last class of lipids that I'd like to talk about are the so-called steroids. And these are made up of a very different type of molecule than the other three classes we've talked about. So in the steroids, there's a 4-ring fused system that exists in all steroids. And these are generally classified as the A, B, C, and D ring. So notice there are 3 6-membered cyclohexane rings attached, and then a cyclopentane ring attached. So the most common of the steroid type lipids is what's called cholesterol. So what we're going to do, we're just going to modify a few things here on this chain to make this become cholesterol. So if I put an OH group here, a double bond right here, I'm going to put 2 methyl groups sort of sticking out like this. And then lastly, we need to put a longer hydrocarbon chain right here, just like that. So this is the molecule called cholesterol. And like the other lipids, it does have a polar head group. So here the alcohol would be the polar head group, and then the remaining part of the chain would be the sort of hydrophobic tail. Now it turns out that the distance between here and here is about 20 angstroms, or 0.2 nanometers. And a lipid bilayer, so we drew earlier, we drew that lipid bilayer like this, or the cell membrane bilayer. Okay, so here's this. These are the long phospholipids. Well, cholesterol likes to sit and reside in the lipid membranes. And so the overall distance of a lipid membrane like this is about 30 angstroms, or 0.3 nanometers. So envision now one of these cholesterols sort of sitting into with our OH up here, and then we've got our other ring systems here. This isn't a very good drawing, but envision now we've got these 4 ring systems sort of embedded into our lipid membrane. One of the main roles of cholesterol is actually to modulate and adjust the fluidity of a membrane. So in general, the more cholesterol that's present in membranes, it tends to make the membranes a little bit less fluid. It tends to make them more compact and a little bit more brittle. Whereas if you lower the amount of cholesterol, it tends to make them a little bit more fluid. That's sort of a general rule of thumb, not always the case, but so that's the molecule cholesterol, and it's classified as a steroid. Now I mentioned that all of the steroids have this basic core feature, the A, B, C, D ring system. If we just do some slight modifications on this molecule, we can make a different steroid that some of you might be familiar with. So I'm going to draw again that A, B, C, D ring system. The A ring, I'm going to actually make a phenol like that. And then everything else is the same. I have my 2 methyl groups, but up here I have an OH. This is estrogen. Again, A, B, C, D. So when the body makes cholesterol, the cholesterol could be used to be inserted into lipid membranes, or alternatively, it could be converted into another steroid like estrogen. I'll just draw one other one. If you were to modify the same ring system just ever so slightly, you get a very different steroid, one with definitely different pharmacological effects. So if we change the A ring from a phenol that's an estrogen to a ketone like this, so that's really the only modification we're going to make. This is also OH up here. This is now testosterone. So just a slight modification of this A versus B ring brings about significant biological differences, basically making male and female in terms of human anatomy. And it's just this slight difference. All of these steroids, though, again, are ultimately derived from cholesterol, which could be brought in from the diet, or there also are mechanisms in the liver and some other tissues, but primarily the liver, to synthesize cholesterol. And those pathways in the liver, those are the targets of anti-cholesterol drugs like Lipitor. They tend to lower the levels of biosynthesis of cholesterol. All right, so that summarizes the 4 main types of lipids. Again, we had fatty acids, we had the triacylglycerides, the phospholipids, and then finally the steroids. All right, so I hope that helps bring some light to the structures of these, and definitely get a little bit more practice looking at and identifying the different types of lipids.